Hello, grade 11s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabutewa Sos Ugobela Wemets. And without any further ado, let's look at these questions that we have here. Ah, Okay, so we have question 3 on Newton's second law. It says a constant force F pulls a 20 kg block at a constant speed over a rough horizontal surface XY as shown in the diagram A below. The coefficient of kinetic friction between the block and the surface is 0.2. So note that. And then 3.1 says give a reason why the coefficient of kinetic friction has no units. Right. So, okay, if we can check here, our reason would be that the coefficient of kinetic friction is a ratio, of two forces. And those two forces we are talking about is your kinetic friction and your normal force. So from Fk is equals to mu k times n. If we wanted to calculate the coefficient, we would have to say mu k is equals to Fk over n. Now we know that the Fk has an SI unit of newtons, and then also the SI unit for normal force is newtons. So now what will happen to the SI units? They would eventually have to cancel out. Let's say maybe, for example, we had 20 newtons for this one, and then we had 80 newtons for the normal force. Then obviously the two would end up cancelling, and then the answer that we'd have here would have no SI unit because it would represent the ratio of the Fk to the normal force, right? So ratios do not have any SI units. Okay, so that's all you were supposed to say regarding that one. Then we go to 3.2. It says draw a labeled free body diagram showing all the forces acting on the block. Now you can either draw your free body diagram like this, whereby you won't be resolving any of this force here, your force applied. So this means you will have your normal force up there, and then down here obviously will be your gravitational force, and then you will have to have your force applied in that angle of 35 degrees, and then opposing the direction of motion would have to be the kinetic frictional force. So let's label here, and then we have force applied. Or if you prefer to resolve, then this is how your free body diagram will look like. So if you do resolve, then you have to consider that you have to resolve your force applied into its components, which is Fx and Fy. So that means this is how it will go. And then this would be your Fx. And then also you'd have to indicate a force going upward like that. So like that. And then let's make this one bigger here. And then also we have our Fk. Then, okay, we would label this is Fk, this is Fg, this is the normal force, this is Fy, and then this here is Fx. Now, note that when they mark these ones, they mark them as 1. So every time you are resolving, you must make sure you have Fx and Fy. So these are the two components that represent this resultant vector here. So putting Fy and Fx is the same as just having your force applied here. So these are the components and this is the resultant vector. So you must always be careful. If ever you do this one, then you must make sure that you don't show the components. If you show the components, then make sure that you are not including the force applied. So it's either this way or that way, right? And then now, 3.3 says state Newton's first law of motion. So how do we state the first law of motion? We will have to say, it says a body. So for 3.3, Newton's first law states that a body will remain in its state of rest, or uniform motion unless a non-zero resultant force acts on it. A non-zero resultant force acts on it. Now, others might say an unbalanced net force. It's still the same thing. If you say non-zero or unbalanced resultant force or unbalanced net force, that's still one and the same thing. A body will remain in its state of rest or uniform motion unless a non-zero resultant force acts on it, right? Okay, then that's our Newton first law. Then, okay, now 3.446 marks says calculate the magnitude of force F. Now, for that one, we would need to redraw our free body diagram. So we had normal force there. And then let's try to resolve. We have Fx, and then this will be Fg. And then this would be our Fy. And then here we'd have our Fk, right? So let's indicate like this. So Fn, Fy, Fx, and then Fg, and Fk, right? So to find air force F, note that we are given that this is moving at constant speed, and we know that this is a keyword to us. Once we see constant speed, we know that our acceleration is 0 meters per second square, which follows that even our F net would have to be equated to 0 newtons. So first, we would have to say 3.4.1 F net is equals to ma. But then because our acceleration is 0, then we have to break down here. What are the forces that will be representing our F net? Remember, we have to only consider the horizontal forces. So this here is the positive direction, and this here is the negative direction. Remember, I did state that the negative direction, you will see it by Fk. So wherever you have the kinetic friction, that's the opposite direction of motion. And your positive direction is always the positive direction of motion. It is the motion, or it is the side where your object is going. So this object, when it is pulled at an angle here, it will be going to the right. So that means your right is positive and your left is negative. So now in presenting this, I will say this is Fx minus Fk is equals to 0. Remember, acceleration is 0. If we say m times a, that's 0, right? So let me just indicate that so that we are all in the same page. So this is mass multiplied by an acceleration of 0. Now, if I have to represent my Fx, I know that Fx is F cos theta, but then I know that Fk is mu k times n. Note that we are only given the coefficient of friction as 0.2 here. And then this is 0 here. Okay, so we will have F cos, the theta is 35 degrees. And then we have our mu k as 0.2. But then now our normal force here in this case, our normal force, because this is being pulled at an angle, if we are to equate the vertical forces, you do understand that this is normal force plus Fy is equals to Fg, which we're then going to end up having Fn is equals to Fg minus Fy. So this is when it's being pulled at an angle. So that means I can replace this. Remember, Fg minus Fy is the same as mg minus F sine theta. So I will replace this by mg minus F sine theta, and then equal to 0. Now, cos 35 degrees, if I punch it into my calculator and just round off to 2 decimal places, so I will say cos 35, and then it gives me 0.82. And then let me say F minus 0.2. My mass here is 20 kg, so I will have 20 times 9.8, and then minus F, and then sine 35 degrees is equals to 0. So this is 0.82F, and then minus, this is 0.2 times 20 times 9.8, and then this is supposed to give me 39.2. And then if I do this one, if I just take this here, negative 0.2, and then cross multiply, and then multiply inside, with the negative F sine 35, then obviously it will be negative 0.2 times sine 35. And that will give me positive 0.11 rounded off to 2 decimal places and then F, right? So I'm just trying to make things simple here by just rounding off the decimals to 2 decimal places. Then 0.82F plus 0.11F is equals to 39.2. Now, if I add these ones, 0.82 plus 0.11, this is going to give me 0.93F is equals to 39.2. And then dividing both sides by 0.93, 0.93, then my F is supposed to be what? 39.2 divided by 0.93. This is going to give me 42.15 newtons. Okay, and that's it. That's it. That's how you were supposed to calculate that up until you arrive to that answer there. Okay, then let's proceed. We have 3.4.2. It says calculate the normal force. So now that we have this force here, 42.15 newtons, we can now easily calculate the normal force, right? So we can now easily calculate the normal force by simply saying the normal force in this case should be Fn is equals to Fg minus Fy, which we did say it's mg minus F sine theta, right? And then our mass is what? Is 20 and then times 9.8 minus, remember we already have the F, so we'll say it's 42.15 and then sine what? 35 degrees. Then all you have to do is punch all of that into your calculator. So this will give me 20 times 9.8 minus 42.15 and then sine 35, right? And then this is going to give me 171.82 newtons, right? So rounded off to 2 decimal places. And then if I'm looking for the frictional force, 3.43, and then Fk, I do understand it's mu k multiplied by the normal force. So our mu k is 0.2. We already have the normal force from up there, 171.82, right? And then if you multiply that, so I'm going to take the 0.2 multiplied by 171.82, and then this is going to give me 34.36. So 34.36 newtons. Okay, and then that's it. That's it. So, okay, we have 3.5. It says the same constant force is now applied to the block over the same rough horizontal surface as before at an angle of 15 degrees with the horizontal as shown in diagram B below. How will the frictional force of block B in diagram B compare with the frictional force of the block in diagram A, right? Only higher than, lower than, or remains the same. Now, here you must understand that when it comes to friction, the lower the angle of the force applied, the lower the angle of the force applied, the greater the frictional force. The greater the frictional force. Now, with this knowledge, we can tell that obviously the frictional force acting on diagram B would have to be greater than the one acting on diagram A. So our answer here would have to be higher than. But then now, if you don't want to take my word for it, you can still try to calculate and prove for yourself. So let's say, remember, we did find our frictional force in the previous question, and then we said it was something like 34.36 newtons, right? Now let's calculate this one and see if it will be greater than that. So we'll just say Fk is equals to mu k times n. We haven't changed the surface, so our coefficient would still have to be 0.2. And then this would have to be mg minus f sine theta, right? So we are keeping everything constant besides the angle here. So our mass 20 and then times 9.8 and then minus F, we'd still have to write the same force that we found, so which was 42.15 meant to say 42.15 and then sine 35 degrees. And then if you were to punch all of that, it's 0.2 in bracket 20 times 9.8 minus 42.15, then sine 35. Then let's check. We are getting what? We are getting... Okay, so it's not sine 35 anymore. It's sine 15. Pardon me for that. So, okay, then 42.15 sine 15. And then let's go and change it there and see what we find. So this is going to give us 37.02 newtons, which obviously compared to this one, we can see that the Fk at diagram B is greater than the Fk at diagram A. So that means we are correct in saying higher than. That's how you were supposed to tackle this question for a total of 19 marks. So you know what to do. If you have enjoyed the lesson, please press the thumbs up button, and then always remember to share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning SAT.